Hello and welcome to the video demonstration of the bulk localization workflow series. I am Pratyush Banerjee from DCU, and I am going to take you through this demonstrator titled Domain Adaptation and Inline Markup Support for Statistical Machine Translation. As the title suggests, this demonstrator showcases two different aspects of statistical machine translation. Domain adaptation, particularly for a scenario where sentences to be translated come from a mixture of different domains, and support of translating data with inline markup directly in the workflow of statistical machine translation. The domain adaptation scenario is particularly relevant for the translation of specific enterprise content, where there might be a dynamic mixture of different domains in the data. On the other hand, the inline markups are extensively used nowadays, not only in the localization industry, but also a lot of other industries to ensure formatting, metadata content, etc. Hence, using statistical machine translation to directly handle data with inline markup has a considerable impact on the localization as well as other industries. For the domain adaptation demonstration, we start with the software documentation sentences in French. These sentences, what you look at in the screen, are sentences from a mixture of two different domains, developer and end user. The domains have evidently been decided on the basis of the target audience these documentations are meant for. So basically, we have sentences from the end user domain and the developer domain combined together, and we want high quality translations of them into English. This particular demonstration uses statistical machine translation as the main technology. Machine translation usually is a background process, and it is hard to properly demonstrate this in a particular scenario. Hence, we have relied on the workflow visualizer to show us exactly what happens behind the scenes. Our research has revealed that instead of using a single statistical machine translation model trained on the combined data from both the domains, using domain-specific engines and training separate models using them generate better results in the given scenario. Hence, we have trained two separate engines, Empty Engine 1 and Empty Engine 2, for the two different domains. Empty Engine 1 has been trained on the developer domain, Empty Engine 2 has been trained on the end user domain. The classification module here is actually a statistical classifier which predicts the domain of an input sentence. Depending on this classification, the empty selection module routes the particular sentence either to Empty Engine 1 or Empty Engine 2 for translation. If you look at an example, for this particular input sentence, the classifier says that this is a developer domain sentence, and depending on that classification, the Empty Engine 1 is selected by the empty selection module, and Empty Engine 1 actually generates the translation. Similarly, if we look at another example, this particular input sentence has also been tagged as a developer domain data by the classifier. The empty selection module, as in the previous case, selects Empty Engine 1, which however generates the translation. If you look at another sentence here, in this particular case, the classifier says that this is an end user domain sentence. The empty selection module now selects Empty Engine 2 for its translation, and the Empty Engine 2 actually translates this particular sentence to English. Looking at another example, this particular sentence is also tagged as end user, and empty selection module selects Empty Engine 2, which actually generates its translation. The advantage of combining two domain-specific engines using this particular configuration is not only in terms of quality but also in terms of maintainability. In terms of quality, the quality of this translation, as you can see on the screen, is as good as if we would have used a single empty engine trained on data from both the domains. However, from the point of view of maintainability, this becomes much more easier since this allows us to add in or take out domain-specific engines depending on the availability of data. This is also particularly suited for translation of small-scale translation jobs suited for very narrow domains where we do not need bigger general domain engines. These not only gives us ease of maintainability but also saves a lot of memory and CPU since it uses smaller models instead of larger ones. Another aspect this demonstrator showcases is the handling of inline markup directly in the standard workflow of statistical machine translation. As you can see in the screen, the input sentence has a lot of inline markup, which has been quite successfully translated in its English counterpart. Traditionally, inline markup has been handled by replacing the markup tags with placeholders in the pre-processing step. Then, after the sentence has been translated by the machine translation, the placeholders are again replaced by the markup tags in the post-processing step. However, when there is a lot of reordering happening between the words or phrases between the different language pairs, the tags tend to get placed in the wrong position within the sentence. To avoid this particular issue, we experimented by directly training machine translation engines with marked up tagged data. Our research revealed that the crux of markup handling lay in the tokenization step of this input sentence that happens before training. Hence, we experimented with two different tokenization schemes. The two different tokenization schemes were the normal complete tokenization, which is generally a part of the standard workflow of statistical machine translation, where every part of this particular sentence is tokenized, including the tags, and a partial tokenization, where every other part of the sentence is tokenized, excluding the tags. If you look at the example in this particular input sentence, in case of complete tokenization, all these tags have been tokenized. However, in case of partial tokenization, the tags have not been tokenized, but everything else has been. Usually, since the tags always come from some standardized format like XML, TMX, HTML, etc., hence identifying the tag set during tokenization is pretty easy. Hence, we observed that using the partial tokenization allowed standard statistical machine translation engines to handle marked up data very well, as is shown in the given translation. That brings us to the end of this demonstrator video. Thank you for watching. In case of any further questions regarding this particular demonstration, please contact me at my mail address pbanerjee@computing.tcu.ie. Thank you.